Here's a quick video for you on molecular geometry. However, I'm going to steer us in a little bit of a different direction first because I think it'll ultimately help you understand the different shapes a little bit better, right? There's something else called electron domain geometry or electron pair geometry. It goes by a couple different names, but it is basically based on the number of electron pairs attached to the central atom. And I think that that is useful because there are fewer electron domain geometries than there are molecular geometries, because molecular geometry looks at how many are shared, how many are unshared. So I think that one of the easier ways for you to understand the molecular geometry is to know the big categories of electron domain geometry. And your big category, so first of all, electron pair geometry is just based on, or electron domain. And the difference between domain and pair, just so you know, is like I said in class, a double bond is regarded as one electron domain. So even though that's technically two pairs being shared, because those two pairs are attaching to the same atom, it's viewed as one like bonding area for the purpose of deciding molecular shape. Okay. So that like electron domain might be a better word for that reason than electron pair. But all right, so electron domain geometry looks at the total number of electron pairs or domains coming off the central atom. Okay. It doesn't matter if they're shared or unshared, you're just doing the overall count. All right. So for example, skip down here to water, which I drew for you. If you look at water, it has two shared pairs and two unshared pairs. So we would consider that to be four electron domains. Okay. Um, there are only five possible electron domain geometries, and those five are linear, trigonal planar, tetrahedral, trigonal bipyramidal, and octahedral. Okay, so those are the five main categories. You've learned a little bit about linear, trigonal planar, and tetrahedral. Trigonal bipyramidal and octahedral are for expanded octets only. Okay. All right, so going back to water, we would say it has four electron domains, two shared, two unshared. Okay, we'll just keep that in mind. Um, so here are your electron domain geometries. Okay, so you can see linear has two sets of electrons coming off the central atom. Trigonal planar has three. You can see your bond angles over here. Remember, that's part of your chart also. We will talk more about bond angles during our next class period. So if you want to try to fill it in for these, you can, but you might want to hold off. Tetrahedral is four electron domains. Five electron domains is trigonal bipyramidal, and six electron domains is considered to be octahedral. Okay. The reason I'm showing you these is because then I think it's easier to understand that molecular geometry then starts to look at, okay, how many shared versus unshared pairs are we dealing with? Okay. So if you have an electron domain geometry of linear, your molecular geometry also has to be linear because you only have two sets of electrons coming off the central atom. Now, in this example, which I like, they used carbon dioxide, and I think that that is useful because then you can see that, like, even though that's two bonds, it's considered to be one domain because there are electrons being pulled towards oxygen, and over here there are other electrons being pulled towards oxygen. So those are considered to be two domains instead of looking at it as like four shared pairs, if that makes sense. Okay, so that's linear because you have two sets of electrons coming off carbon in different directions, okay? All right, now if you get to trigonal planar, here's where your options come in. For an electron domain of trigonal planar, you can either have 3 shared pairs and 0 unshared, or, and they call them like bonding and non-bonding, but bonding is shared, non-bonding is unshared. Or you can have 2 shared, 1 unshared, okay? So if none of your electron pairs are unshared, so no dots on the central atom, then the molecular geometry matches the electron pair geometry. Okay, so trigonal planar is still trigonal planar if there are no dots on the central atom. What if there are dots on the central atom? Okay, well then it ends up being bent. Why? Because these domains, the unshared pairs, take up more space than the shared pairs, okay? So they are actually able to decrease the bond angle a little bit between these shared pairs, okay? So that's really what these molecular shapes are about, is it has to do with the bond angles around the central atom, but unshared pairs are better at repelling the shared pairs. And the reason they're better is because they're not stuck between 2 atoms. Like they can actually push a little bit more than these bonds can, because those bonds are pretty rigid because they're stuck between 2 atoms, okay? So what ends up happening is, you know, for example, trigonal planar has a geometry like, or a bond angle of 180 in a, or 120, I'm sorry, not 180. Linear is 180. Trigonal planar is 120, but in a bent molecule, it's actually going to be a little bit smaller than 120, because that unshared pair is going to do a better job of pushing these 2 bonds closer to each other. And so they're not as far apart as those 2 were, if you can kind of see that, okay? All right, so then your next one is tetrahedral. And obviously, like, the more domains you have, the more options you're going to have for shapes. So again, like tetrahedral will be tetrahedral if there are no unshared pairs on the central atom. So so carbon's a great example because typically it's bonded to 4 things. That's going to be tetrahedral. When it starts to change is when we add unshared pairs to the central atom. So nitrogen, for example, typically has 3 lines and 1 set of dots. Well, that 1 set of dots pushes those 3 lines closer to each other. So that's considered trigonal pyramidal. Then you can also have oxygen, which has 2 unshared pairs and 2 shared pairs, like in water. Well, now it has 2 unshared pairs on it, which means it's going to be even more effective at pushing those shared pairs closer to each other. That's a 2 and 2 situation for electron domains. So that's considered to be bent, okay? So these are your options when you have 4. All of these you learned last year. The new thing to you are these expanded octets, and they do exist, okay? So sometimes you might have 5 electron domains. 5 electron domains has an electron pair geometry of trigonal bipyramidal. If it's 5 and 0, it's trigonal bipyramidal. If it's 4 and 1, it's considered seesaw. Okay, and we'll talk a little bit about why it's a seesaw. I don't think their drawing of it does a great job of showing you. You can have 3 and 2, which is T-shaped, and you can have 2 and 3, which is considered linear. Okay. And then sometimes you might even have 6 electron domains coming off the central atom. Okay. So that's considered octahedral. So if it's 6 and 0, octahedral. If it's 5 and 1, that's called square pyramidal. And if it's 4 and 2, that's considered to be square planar. Okay, so you can use these to help you figure out the molecular geometries. That's what I asked you to do on your worksheet. So you're just looking at this bar column over here to decide the molecular shape. Okay, and then we'll discuss them in more detail next class.